Okay, good afternoon everyone. Welcome to today's special colloquium by Professor Arif Babul. It is my pleasure to welcome you to this colloquium and to introduce Professor Babul to you, who is an university distinguished professor at the University of Victoria. He is also currently the Infosys visiting chair professor at IISc. Before his position at University of Victoria, he started his career in Princeton with Jerry Ostriker, right? He did your PhD with Jerry Ostriker. Sad news that he passed away recently. Then he was a postdoc at University of Cambridge, and then moved as an assistant professor at New York University for a year or two, I guess, and then finally settling down at the University of Victoria. Professor Babul is an expert in computational astrophysics, particularly formation and evolution of large-scale structures like galaxies, clusters of galaxies, supermassive black holes, and related topics. He has always pushed the boundaries of the structure formation and the formation of these large-scale structures, challenged the postulates for many decades, and provided very useful insights into the formation of clusters and diffuse gas in the clusters. We'll hear more about it now. In recognition of his work, he was awarded David H. Turpin Gold Medal in 23, and he was also elected as a Fellow of American Physical Society in 23. Apart from computational astrophysics, as many of you have conversed with Professor Babul, he is also interested in doing research in, I think I can say that now, in India, right? Right. He has an interest in computational neuroscience, interface between quantum computation and turbulence, applying machine learning, artificial intelligence in astrophysics and other topics. So let's welcome Professor Arif Babul for today's colloquium. Thank you.
Thank you very much, Karthik. And it's a pleasure to be here. It's a pleasure to actually return here again. I was first here in 2007. I wish I had more time. I'm leaving tomorrow, but I've discovered so many interesting research areas going on that I would have loved to have spent 2 or 3 days wandering around the different labs. So I know that there are undergraduate students in the audience, and I know that there are people who are not necessarily astrophysicists here. I have written my talk specifically so that it should be accessible to most people, and it should be accessible to most of the undergraduate students as well, for the most part. And if it's not, ask me questions. All right, so my title of my talk is Supercomputing the Universe. Let's start with the outline of what I will be discussing. Am I standing in the right place? Maybe I should stand over here as long as this thing works for me. So I will start by giving a brief observational overview of cosmology and large-scale structure, basically a summary of where we have gotten over the course of my academic career. And then identify and discuss modeling of physics of cosmic structure formation, and then share with you some of the progress, but also some of the challenges. I'm not here to sell you on a particular method. I'm not going to tell you that, Romulus or TNG or Simba is the best thing since sliced bread. I'm here to actually inspire the younger generation to work on this, to show you that the problem has evolved in leaps and bounds, but there is so much more work to be done and so much more interesting work to be done that you should be looking at the challenges as much as the progresses themselves. So just 3 decades ago, our understanding of the physics of the universe was incredibly uncertain. This is when I was in graduate school. the age of the universe was estimated to be anywhere between 7 and 20 gigayears, right? We knew that the baryons, stuff that we are made of, make up a minor component of the total matter in the universe, but the amount was highly uncertain. And this was a fun time to be a theorist. Data was sparse, and you could be incredibly creative. And so models of everything, including the large-scale structure and the expansion of the universe and evolution of galaxies, were highly imaginative, but very simplified. All right? Spherical cow was the name of the game at this point in time. And of course, best thing for a theorist, largely untestable. In fact, just to mention, you know, when I was at Princeton shopping around for a thesis project, one of the topics that fascinated me was plasma physics, you know, whether it's cosmic plasma, but at that time, a lot of activity was going on in solar physics, and so coronal plasma, solar wind plasma. I spoke to several professors, and Jerry was the one who said to me, no, you don't want to work in that. That's a bad idea for a theorist. Too much data. So with that, it's in the 1990s, around the time 1989 or so, when the situation started to change dramatically, in fact. First of all, at the Bell Labs in New Jersey, people had developed digital film. Today, these particular devices are in all of your phones, the charge couple devices that you use to take pictures. But back then, they'd just been developed. And the solid state people who had developed them had managed to get them to about 50% quantum efficiency. And then the challenge for Bell Labs and the rest of the research group was, how do you improve this? Now, they didn't want to invest their time, so they handed it over to the astronomers. They said, you know, you've always been wanting to have digital film at the back end of a telescope. Well, here's your chance. Play with this. And that's exactly what they did. They played with it. And people like Tony Tyson and Anthony Stark and company raised the quantum efficiency up to about 90% over a span of a few years. And soon enough, CCD arrays were put on back ends of telescopes. And digital images were now starting to come online. And over the course of the time from 1990s to today, we've developed powerful telescopes, and the field has essentially gone from being data-starved to data-rich to, I would even argue, data-overwhelmed at this point in time. There was a second development that started along the same time. Powerful new computers, both storage devices as well as high-performance computing CPUs, very fast CPUs, were starting to be developed. Convex was amongst the very first such machines that came online, but very soon there were IBM supercomputers that came online. And you know, most of you may not be aware, but in North America, when companies like IBM developed new supercomputers, the first group of people they handed over to is astronomers or astrophysicists and climate scientists. Those are the two groups that actually get the first shot at playing with these computers, partly because we're dealing with an incredibly complex system. So as theorists, the kind of problems which I will be describing challenge the fastest computers around. The data itself was coming off online from these various telescopes really started to define big data. And they too could break these machines. And so this is where everything was starting, and there was a convergence that was happening. And so now the first question is, what have we learned from all of this convergence? Well, the first thing that we have learned is that galaxies come in a variety of shapes and sizes. We have galaxies that take on the shapes of flattened systems. Think of pizza slices, except that instead of dough, you have stars, right? You have galaxies that are shaped like this. Within these galaxies, you see all sorts of patterns, spiral arms, bars in the centers. And so understanding the morphology of the galaxies and the origin of all of these different kinds of patterns becomes a problem in and of itself. You have galaxies that look like balls of stars. They're spherical. And so you have a completely different category of galaxies over here. You have a transition going from one to the other in some morphological sense. And then on top of that, we have since discovered that every galaxy has one massive black hole in its center. So trying to understand this type of zoo of galaxies that is populating the universe is a question in itself. How do galaxies originate? What is the physics that shapes galaxy formation is an important problem. And then, of course, galaxies themselves are considered to be the building blocks of cosmic structure. Now, that's sort of misleading in a sense. I will describe a short while in that the building block, the actual skeletal structure of the universe is defined by something else. But galaxies are the most obvious things we can observe. And so they become the tracers of the large-scale structure. And so in trying to understand how galaxies are distributed, we are getting a sense of how matter in the universe is distributed. And then the question arises is how did this arrangement actually come to be? So let's consider the distribution of galaxies in the universe. So this is an image from the 2-mass survey. The 2-mass survey is a survey of bright galaxies. In this particular image, with the exception of the band that's running down the middle here, most of the dots in this image are galaxies. And there are 1.6 million galaxies in this image. Now, HST, the Hubble Space Telescope, has gone much deeper, has gone much fainter, and counted many more galaxies. And when you look at the surveys that have been taken with the Hubble Space Telescope, the indication is that there are more than 250,000 galaxies in the universe. So at least that was the indication when Hubble was around. Now, with even fainter surveys that have been done, we think that the number may be close to 1 trillion. So this is an evolving target. As we get fainter and fainter, we see more and more. So that's something to remember. The numbers themselves here are not something to take on board in a literal sense, but it gives you a sense of how immense the universe is, and that we are trying to understand the entirety of cosmos. That's the kind of work that I do. These galaxies are distributed. So this image is equivalent to me taking a picture of this room and compressing it, so me not being able to tell who's in the back row and who's in the front row. Everything is squished, right? It looks pretty smooth. Yet, if I was able to figure out who's further back and who's in the front, the image changes completely. Our understanding starts to vary. What you see here, as these different images flash, the colors are coded according to distance. And what you see is that the galaxies are distributed in this plane in chains. There are filaments that stretch across the entire skies. There are regions where there is heavy concentrations of galaxies, particularly where filaments cross. And then there are regions that are empty of galaxies. These are voids, what astrophysicists or astronomers will call as cosmic voids. They exist. There are regions that are completely devoid of galaxies. So when I said a few minutes ago that we want to understand the arrangement of matter in the universe, what we really want to do is understand how this kind of topology of matter actually came into being. If you want to think about how this is, in more of a concrete sense, take a sponge and cut the sponge in half and look at the two sides, the holes and the arrangement of matter. That is the kind of universe we live in. We live in a spongy universe. And the question is, how did we emerge? How did we get to this spongy universe? And I keep asking how, but I'll tell you in a second where we think we started. And so that makes it even more of a puzzle. Okay, so this is a picture that has all of those slices of the galaxies superposed, and you can see these patterns, these filaments that stretch across vast regions of the cosmos. You see concentrations. And if I was to take that same distribution now, let me go across the sky like this, take a little slice, and look at all the galaxies in that slice and map out their distance. The further they are, the further back they will get plotted. You can see that sponginess of the universe now. These are 3 different slices of the universe mapping out. We are sitting in the center. The distance further away is in the direction of the laser pointer as I'm showing it to you. And what we see is this universe that looks very much like it's got holes in it, matter arranged around these holes. It is a spongy universe. And in fact, the topology of this universe is more or less has been categorized as something akin to a sponge. I mentioned this, that there are structures in the universe that are massive concentrations of galaxies. Here are just examples of some of these systems. They range from something equivalent to, 1,000 billion times the mass of the sun to 1,000,000 billion times the mass of the sun. So we span a huge range in terms of the sizes and the masses of even these most concentrated, heavily concentrated objects. And these are just 2 images that show you what they look like. These clusters, these regions that occupy these nexuses between filaments span several million light years. They contain mass equal to 10 to the 14 or 10 to the 15 solar masses. And the galaxies are in fact whirling about. They're moving around at anywhere from the smallest objects have galaxies moving around at about 300, 400 kilometers per second. The largest have galaxies moving around at 1,000 to 2,000 kilometers per second. They are swirling around, but they do not escape. In fact, one of the earliest questions that was asked when this motion of galaxies, concentrations of galaxies, and the motions of the galaxies were measured, it was Zwicky who asked the question, why are these systems not flying apart? And the answer is they're trapped by gravity. But the question is, where is this gravity coming from? If you add up all the mass that you see in the light and you associate gravity with that, it's not enough. There isn't enough gravity associated with visible matter to actually hold these systems intact. This was the first indication that there was something else in the universe apart from the ordinary visible matter. This discovery, and now it's been sort of reinforced repeatedly over the years through things like gravitational lensing measurements, that there is much more gravity present. The study of light element formation in the early universe allows us to place very strong constraints on the amount of ordinary baryonic matter, stuff that you and I and the Earth and the stars are made of. And we know that whatever there is can't be baryonic. And so the word, the label that astrophysicists and astronomers attach to this is dark matter. And there are, attempts to try and understand what this dark matter is. I will avoid that question, but there are experts in the audience here who can probably answer your questions more effectively than I can. But the idea that there is that there, for every atom of ordinary matter, there is about 6 times as much invisible matter is one of the foundational developments in cosmology and in structure formation. And a way to think about it, here you are, living at the edge of the Himalayan range. Way to think about it is as you move up north and you go to the foothills of the Himalayas, and then you continue further and further up, you will see, first of all, mountain ranges that are completely snow-free. Imagine that you couldn't see anything unless there was snow on it. So mountain ranges that have absolutely no snow is invisible to you. Mountain ranges where only the highest peaks have snow in them, you'd see the peak, and that's it. You wouldn't see the mountain. And then as you go further up, you'd see more and more. And so essentially, what I'm asking you to do is imagine that you can only see the snow-covered peaks, but not the bulk of the mountain, nor the peaks that are bare. The question is, we now know that the skeletal structure of the universe is formed by these bare peaks. It is the stuff that we cannot see that lays down the large-scale structure of matter. And the question is, again, to repeat, is how did this whole system sort of emerge into that form? Just to give you an idea of what I mean by this dark matter, this is the artist's rendition of what our Milky Way looks like. The Milky Way galaxy is a galaxy that we happen to be living in. It has a shape that is something like this. It's a disk galaxy with spiral arms. It is sitting at the center of a gravitational well. The well is created by a distribution of dark matter, and the extent of the dark matter in some sense spreads out roughly about a factor of 10 in radius, more than the galaxy itself. Right? So we are sitting in a bowl of dark matter. At the center of this bowl of dark matter lives our galaxy. And all the galaxies follow this particular distribution. And then these dark matter bowls are arranged in patterns across the sky. The next thing to remember, the next thing to take on board is that as we probe fainter and fainter, as we look further and further back in distance, we are actually looking at the universe further back in time. Light takes a finite amount of time to come to us. It has a finite speed. So if you look at the sun, what are we doing? How far back are we looking in time? Yeah, 8 1/3 minutes. So we're looking back at the sun the way it was 8 1/3 minutes ago. If the sun was to blow up, it would take 8 1/3 minutes at the very least before we would feel it, before even the Earth's orbit would be affected. So as we look back with our telescopes, we are seeing the evolution. We look at slices of the universe as we're going back in time. The furthest back we can see is about 375,000 years after the Big Bang. We see the afterglow of the Big Bang itself. And we can see patterns in this afterglow of the Big Bang. And beyond the patterns, we see the beginnings of star formation and galaxies starting to emerge and then evolve forward towards the time. So in a sense, this is what people who study climate would go to the South Pole or the North Pole, and they would drill into the ice core and take out this core and look at the layers of the core and figure out what's happening at different points in the Earth's history in terms of the climate. Here, a telescope beam is in fact like a core that's drilling through the universe's past. And we are capturing the history of the universe as it was back in time. This is the first sort of developed detailed measurement of the microwave background, again, happened around 1990s. It was by the COBE experiment. It was the beginning of the age of precision cosmology. And this is the first image that came online. It shows you this dipole motion or a yin-yang pattern. The yin-yang pattern, the dipole motion, the dipole pattern is reflective of the fact that Earth is moving around the sun is moving around the galaxy is falling towards its sister galaxy, the Andromeda galaxy, and together, the Andromeda, the Milky Way, and its collection of smaller galaxies were all falling towards a cluster called the Virgo cluster. Take out their velocities. We know how to do that. So if you take out their velocities, this is what you get. This is now, I've put down here not only the results from COBE, but also results from WMAP, which was an experiment that came about 10 years later. and Planck, the most recent space-based microwave background experiment, which came again 10 years later. And the first thing you notice is that it's not smooth. It is not smooth. There are patches of hot and cold. These patches of hot and cold are roughly about 1 part in 100,000. So they are extremely small fluctuations. One way to sort of imagine how challenging and how difficult and how amazing this feat is to imagine a lake that is absolutely still, pluck out your hair, throw it onto the lake so that it's floating. That little bump, step away about 1 kilometer and see if you can see it. This is how difficult, how challenging, and how incredibly amazing it is that we can look back at the universe and pull out these kinds of fluctuations. Now, COBE showed these fluctuations at its own resolution. WMAP has much higher resolution, and Planck has higher resolution. Yet, when you take this kind of a map and you decompose it into wave modes, Fourier analysis, or in this case, spherical Legendre polynomials, what you end up with is a map that tells you where the fluctuations tend to go up and down, a power spectrum, if you will. And you see peaks in the power spectrum that look like this. Now, I don't think the plot here gives you a very good sense, but the WMAP, which is green, barely made it out to about past the third peak. Planck made it out to over here, but now we have ground-based telescopes, one of which is based in a high mountain plateau in Chile. The other one is in the South Pole. And these experiments have been able to push the microwave background power spectrum analysis all the way out to very large modes. Very small modes, I should say. Now, what do we learn from this? Well, what we learn is that this shape of these patterns and the amplitude of these patterns are related to both astrophysics as well as cosmological parameters. So I mentioned at the very beginning that the age of the universe was highly uncertain. I mentioned that we did not know how much matter there was in the universe. I mentioned that there was a lot of uncertainty in various parameters that described our universe. Well, here's an illustration that tells you what happens. So if I take the total amount of matter in the universe, and I just simply scale it up and down, and I ask, what happens to this microwave background power spectrum, you can see visually what's happening. First, the shape of the primary peak moves up and down. Secondly, the ratio of the primary to the secondary to the tertiary peak is changing. So just the relative amplitudes of the peak gives you a direct handle on how much matter there is in the universe. This is similarly showing you what happens when you vary the amount of baryonic matter in the universe. And again, you see various changes happening. One thing you cannot see easily is that the shape of, the position of the peaks also vary somewhat, and the positions of the peaks are highly sensitive to the geometry of the universe. And so basically from something like this and doing a full detailed analysis of the microwave background, you get to learn a lot about the details nature of the universe. We now know how much matter there is in the universe. Of the total amount of matter energy in the universe, dark matter and baryonic matter together make up about 1/3. We know, for example, that the age of the universe is 13.76 billion years. We know that the fluctuations that you saw in the microwave background, what their shape is and what the amplitudes of those fluctuations is. And we also know what the shape of the space-time is. The large-scale structure of the universe is flat. Now, if it's flat, it tells you that if the total matter content is only 1/3, and that includes dark matter, by the way, and if the shape is flat, it tells you there's something else in addition to that. And this is where the idea of dark energy sort of started to fly around. And then there were other experiments that were done that suggested indeed that dark energy was there and started to describe the expansion of the universe, something that I will not go into too much detail here. But this sort of schematic tells you various parameters that the microwave background and combination of microwave background with other experiments have managed to pin down. We have now reached the age of precision cosmology. Experiments like Euclid and LSST and DESI, these large telescope survey experiments, have been promising that we'll be able to get down to 1% accuracy, precision, and even sub 1%. So remember, we were at a point where we didn't know that the universe was between 7 and 20 gigayears. We're now talking about sub percent precision in the span of about 30 years. So this is how far and how fast we have come in terms of understanding the cosmos. These fluctuations reflect quantum noise. At least the hypothesis is that they reflect quantum noise generated in the very, very, very early moments of the universe when the universe was inflating very rapidly. And the quantum noise fluctuations, although being generated on atomic scales, were being expanded, stretched to beyond the size of the universe's horizon and then frozen in. And then eventually they caused, they became the seeds of the observed structure in the universe. Now, to understand what I mean by seed, if the universe was absolutely smooth and homogeneous, and I asked you, you're standing there in the middle, and there is equal amount of matter around you, which way would the gravitational force pull you? Equally in all directions or in no direction whatsoever. It cancels out. So in order to take what looks like really smooth matter with tiny little fluctuations and turn it into the organized universe we see today, there had to be asymmetry. There could not be uniform distribution. These fluctuations become those seeds. They create a little bit more gravity here, a little bit less gravity there. Then matter tends to flow that way. And so this is the seeds with which we start. When we start doing our model building, we start with these kinds of fluctuations that are observed in the microwave background at the age of 375,000 years and work our way forward. So we want to understand, how did we go from a universe that was incredibly smooth with fluctuations roughly about 1 part in 100,000 to a universe that looks like this, to a universe that looks like this, to a universe that looks like this. And then in addition to describing the present-day universe, we also want to be able to describe the slices of the universe that we observe as a function of time. The challenge for astrophysicists is that unlike physicists who have experiments in labs, we can't repeat this experiment. We can't experiment, vary things around, and then press a button and start the Big Bang again. That's not a viable option. The second problem that we have is that this is a multi-scale, multi-component problem. What do I mean by that? Well, first of all, I've already told you, there is dark matter, there's baryonic matter. That's just the beginning of it. Next, the physics that describes the evolution of the universe in its full glory spans 30 orders of magnitude, from atomic physics all the way up to things on the scale of 200 megaparsecs, which is the range over which the cosmic gravitational tidal fields shape the matter distribution. So you have to capture that entire span. And capturing that entire span means capturing 30 orders of magnitude. Our numerical simulations, the best we can do is about 8 or 9. So when I say we can break the fastest and the best computers in the world, I'm not joking. We can actually grind them down. So people like NVIDIA give it to us, give these computers to us for free just to see how much we can push them and how fast we can make them work before they break. So, but for us, NVIDIA and IBM is a secondary consideration. The fact that we have so many orders of magnitude, 20 orders of magnitude that remain unresolved is a challenge. We are dealing with a network of physical processes that are interacting with each other in very nonlinear physics. Most of these physical processes span the whole range of physics itself, from atomic, nuclear, all the way up to gravitational. And the way we try and solve this problem, as I said, is through numerical modeling using cosmological hydrodynamic simulations, but with the caveat that you have to keep in mind that we are not able to directly simulate the entire system. Now, before I tell you how we get around that problem, let me describe to you what we can do. We can take dark matter only. Dark matter doesn't interact with each other. It's basically weakly interacting, so if dark matter was to come, it would basically slosh through. Dark matter, as far as astrophysicists are concerned, only interacts through gravity, and therefore I can lay down a pattern of dark matter. So I'm going to click this back on. The movie is starting before I press this button, so it's kind of hard to see. But if you look at the box on this side, just before it starts moving, playing, you will see smudges of blue and black. Blue shows you where the matter was just slightly more concentrated at the beginning of the movie's run. And then gravity does its magic. And that's all it is, just gravity. So you can see what happens. Gravity starts to organize itself. Regions that are slightly more matter-rich will pull in stuff from their surroundings. You will start to get filaments starting to form. You will get where filaments intersect. You will get galaxies forming. This is another version of the same thing. We are seeing a numerical simulation that's contemporary. This is about 25 years old. Resolution is somewhat low. This is an incredibly high resolution simulation, and it's spinning in such a way that, it's designed in such a way that while it's spinning, light is sort of lighting up the structures inside, and you can see the entire box coming into being. But the structures are essentially identical, except that these are much more well-defined now. You are seeing filaments, you see voids, and you see galaxies or dense regions that I will eventually associate with galaxies coming into being. We have a model where if you consider the distribution of matter here and you compare it to the distribution of galaxies, minding of the fact that you are looking at dark matter here and you're looking at galaxies over there, so to some extent galaxies are like tracer particles, what we find is that there is a considerable agreement. So let's see if I can show you. No, I guess not. We find that statistically there is an excellent agreement between the model that we can create in a very simple sense and the observed large-scale structure of the universe. But that statistical agreement on the largest scales where gravity is dominant is not enough, because galaxies may be formed initially via gravity, but they shine due to other processes. Their shapes are set up by different processes. And if we want to understand the morphology of the galaxies, the distribution of galaxies, why why do the biggest objects in the universe not have as many stars as they should have, we have to answer different questions. What do I mean by that? Well, if I go back to the dark matter picture and I ask, what is the number of dark matter spheres of a given mass that populates my universe? I have a function. This is known as the mass function for dark matter halos. If I take the ratio of the dark matter halos, the dark matter to ordinary matter, and I multiply it to the dark matter mass function, I would expect my galaxies to look like this. In other words, if every dark matter halo has its own contingent of baryonic matter, and that baryonic matter turned into stars without any other complications, then I would expect the galaxy mass function to look like this. But the galaxy mass function looks like this. And two things are worth noting. One is at the high mass end, the galaxy mass function drops very steeply. In other words, these systems out here, these dark matter systems, do not form stars efficiently. Similarly, at the lower mass end, the smallest dark matter halos do not form stars efficiently. It's flatter here than over here, and steeper and dropping very quickly compared to the dark matter. So when we compare the visible universe to the dark matter universe, we find some puzzling differences arising. And answering those puzzling differences is one of the challenges. This is another way of thinking about this. If you look at, for example, a Milky Way galaxy, and you look at the satellites that are embedded in the Milky Way galaxy, and you count up how many there are, their distribution is rising steeply towards the small end. But when you do the same experiment with observations, you find that they are not rising as steeply. There is a gap. There is a deficiency of satellites. And the question is, why is that the case? Turns out that baryons are an essential element that have to go into these simulations. Baryons are subject to a whole range of different physical processes. Gas collides. It doesn't go through. Each individual bits of gas do not pass through each other. You have to describe them at the very least using fluid mechanics. Gas has self-gravity. It is subject to the gravity of the dark matter superstructure that's forming. It's subject to cosmic expansion. It shocks. When you squeeze gas, it heats up. When you have water flowing in a river, you see eddies forming. Similarly, gas has turbulence. It is subject to thermal conduction and viscosity. And so we have all these processes that we need to account for. Gas, when it cools in a potential well, will slide to the bottom of the potential well. When it settles and concentrates, it'll form stars. So we have to be able to describe that process as well. Stars, when they die, explode. They heat the gas. They can push the gas right out of the galaxy, and so you can go through what's known as the heating and cooling cycles. We have black holes. Black holes themselves can swallow gas and then eject powerful beams of energy that can drive gas out. And so we have to account for that particular aspect of galaxy formation. Stars and galaxies and black holes have their own dynamics in the sense of how they orbit around, how they settle down into the bottom of the potential. These are all aspects that need to be modeled. I mentioned that stars and black holes eject tremendous amount of energy that leads to the gas heating up, ionizing, and leads to what we often refer to as baryon cycles, which is galaxies tend to breathe, if you will. They exhale and they inhale. When stars explode, they exhale and throw out gas. And then when the gas cools, it comes back in. And you can go through these cycles in trying to understand how these cycles shape galaxy formation. We have radiation processes. We have magnetic fields, cosmic rays, and dust physics, and a variety of others that I have not listed here. In fact, I'm just going to ignore this. Sorry, Karthik. Karthik works on radiation and radiation transfer through kind of stuff that I've been describing, and I'll show you in a second. But that's way too complicated for me. So we will just ignore this. Now, I'm not going to ask you to, think about this very carefully, or even memorize this. I just want to give you a sense. Some things we can do directly. So gravity we can model directly. Some things we cannot do model directly, but we understand the physics really well, and so we can construct models that we can embed inside numerical simulations to capture the physics that we cannot model directly. All right? But then there are stuff that we just simply do not understand well. And that's things like black holes. We just do not understand how black holes here eject energy. How does that energy interact with its environment? And so there, we have to construct some models that capture our understanding today. Often the models are ad hoc in the sense that they are sort of wave your hand. I think this is how it works. I'm not 100% sure, right? If there is a weak link in these models, that's where it is. This is an image from a numerical simulation called the Romulus simulation, which is showing you what happens as a system like this evolves. We've put in all the physics that we could, and what you're seeing is galaxies lighting up along the filaments. And then you have galaxies that have stars that are exploding, throwing a lot of gas out. We have black holes that are exploding, that are injecting tremendous amount of energy and throwing gas out. And so what you end up with is a time history of the universe. And the question is, how does this model work? Or how does it fare? I'm going to skip this. I'm going to skip this too for the moment and skip this. Okay, let's zip in over here. I asked the question, how do such models fare? Well, you can look at individual galaxies in the simulations that are the highest resolution, and I've picked two. TNG 50 is one such model, and the Romulus model is the other one. They have nearly comparable resolution, and they are amongst the highest resolution cosmological simulations that have been run. And what you see is the impressive aspect of these simulations. You are now not only capturing the full morphology of the galaxies, not only do you get spherical galaxies and disk galaxies and everything in between, but you are also now starting to capture the patterns in the stellar distribution itself. You see the bar, you see spiral patterns, you can see flocculent spirals, you can see grand spirals, you even see tidal streams as two galaxies pass by each other, and the gravity of them stretch them out and pull out material. So the full morphological distribution in these kinds of simulations on the scale of galaxy is not just impressive, it actually agrees with observations. We are talking about Milky Way-like galaxies, and we're talking about systems somewhat smaller than Milky Way-like galaxies. We can also capture the large-scale distribution of these galaxies, and that they describe the universe populated by these galaxies incredibly well in the statistical sense. So, we are not simulating a particular aspect of the real universe. Remember, we're doing this statistically, but we can run ensembles of universes. And as we compare the statistical distribution of these ensembles of universes to observations, we find that we are doing incredibly well on this front as well. We can even start to describe how much baryons there are in the universe and within each halo, within each system. And we see that the highest systems have the most baryons, but as you go down to smaller and smaller objects like galaxies, the amount of baryons tend to decrease. Similarly, the efficiency of star formation varies with the size of the halos. We more or less start to capture that feature as well. In other words, the model is doing remarkably well, not just in terms of reproducing the universe, but I hate to say predict. I think the more correct word is post-predict the universe. We are able to describe how the universe looked in the past, and then when the observers get around to observing the universe, turns out that the agreement is remarkably good. Now, I've told you that the models are very good, but there is this aspect of the models where there is a weak link. And that weak link had to do, for example, in these models with how black holes are modeled. We have described, I told you that we did not understand the physics well. Black holes are tiny. Even the most massive black holes occupy the region around the black hole would occupy space smaller than the solar system. And so we cannot even model that directly, much less model regions that are factors of 10 and 100 and 1,000 larger. We still can't do it. We are left with the idea that we have to do some approximations. We are left with the idea that we do not understand the physics well enough, and so we have to then guess at what's going on. And this is where different groups in the universe, even though, different groups around the world, even though they can describe the galaxies equally well and capture the large-scale structure, if you then go in and look at the black hole and its effects on the universe, things look very different. And so this is one of the large challenges in the field, and I just want to illustrate for you how different these universes would look. So these are 4 different universes, 4 different realizations, and you have a simulation here called SIMBA, Magneticum, Astrid, and Illustrious TNG. And what you see is these red plumes are due to gas that is being expelled by these supermassive black holes. And what you immediately start to see is that in SIMBA, the black holes are incredibly aggressive. And Magneticum comes next. And I think it's somewhat of a tie. Maybe Illustrious is the next one up. And then Astrid has the least aggressive black holes. And in fact, I didn't put on Romulus, but Romulus has the least aggressive black hole altogether. So now we have a way to start to at least narrow the range of freedom that we have in terms of modeling these systems. This is telling you that the large-scale distribution of gas in the universe should be very hot at the present epoch. This is something that should be amenable to observations, and people are trying to make observations that will pin this down. So it is through these observations, it is through studies of gas, very high resolution of gas flowing onto black holes, and the after effect of these, the kind of work that is being done, for example, by one of the astrophysicists at the Indian Institute of Science with whom I'm collaborating. These are the kinds of models that give you insight from the modeling and the physics perspective. Observers give you a different constraint, and the hope is here that as the two converge, we will have a better sense of how these models should be working. But the biggest challenge here is the resolution and the physics that we can capture. And I say to you in the beginning, if I was here selling you a specific model, I would have told you all the great things about these models. I wouldn't have pointed this out to you. This is one of the open questions. This is an area that is ripe for people to approach and make contributions to in terms of changing how we understand the details of structure formation in the universe. So I'm going to stop here. I think I have more or less exhausted my time. My summary, we have the study of cosmic structure in the universe has been transformed over the past 3 or 4 decades, largely due to advances that I described earlier. The models that we use to study these cosmic structure formation, it does incredibly well in terms of modeling regular galaxies like our own Milky Way. It also can do extremely well in terms of explaining how these galaxies evolve over time. Something that I did not describe because it would require me getting into a little bit more detail is that as we go to larger and larger systems, we find that the black hole models also start to fail. They show signs of straining and they show signs of breaking. And then at the largest scales, I showed you an example of how different models make very different predictions. And so that becomes a testable aspect. Ultimately, what we want to do is build a holistic model of cosmic structure formation, starting with galaxies, but not just galaxies. This is important because galaxies are shaped by the forces and the environment around them, but at the same time, the physics that happens in galaxies flows out and impacts the environment around it. And so this is a holistic problem. The smallest scales impact the largest scales, and the largest scales, the environment impacts the smallest scales. The goal here is to understand the full system. And so the regime where these systems need to be stress tested is this aspect of holisticness, this aspect that everything must come back and be consistent and self-consistent. All right, so I will stop right here, and I will be happy to take questions. Thank you. Hang on, let's grab a mic.
All right. So just I had a couple of questions. One to do with where the black holes would go into your simulations, because the question is whether you have primordial black holes, or is it in the formation of the galaxies and the galaxy clusters that you actually get black hole formation? That's one. And the second is to do with the role of dark energy, because of course there are these questions which have arisen of late on the tensions, the cosmological tensions that have arisen, because we're not entirely sure that dark energy is actually a cosmological constant or not.
Yes. So to answer your first question, the way in which supermassive black holes particularly form is an open question. It is yet another open question. I sort of highlighted the feedback question, but that's very much an open question. In our simulation, so I'm involved in two of them, Simba and Romulus. Completely different ways of treating how black holes are seeded. In Romulus, we have taken the physical model that has been put out there, that wherever gas is dense and able to cool and collapse, and doesn't have enough metals in it. Metallicity is important because it is a coolant. If there is an efficient cooling system, then the gas can fragment and form smaller black holes. But if it doesn't have a cooling mechanism, then it'll collapse monolithically to form a supermassive seed black hole. So in Romulus, we have supermassive seed black holes that are already of about 1 million solar masses. They are not distributed anywhere specifically. They are distributed wherever stars can form, but where the metallicity is low. And we find them to be present in small galaxies, in big galaxies. They could be multiple black holes in the same galaxy early on. But as the system evolves and galaxies merge, we find that black holes eventually tend to populate the centers of the galaxies. We still have clusters of black holes, but typically they tend to be concentrated in the centers of the galaxies. So in that sense, the observed relationship of black holes versus galaxy properties emerges naturally without being put in by hand. In Simba, it's done the other way around. In Simba, because of poor resolution or low resolution, we wait till the galaxies get up to a certain mass, and then we plunk a black hole in its center. And the way it's plunked in is sort of unsatisfactory or doesn't quite feel right because it's imposing the relationship that we observe. And then if the result comes out that the relationship is right, it's not a surprise, right? It turns out that there is an attractor. No matter how you start, it always ends up in that relationship. But this is completely an open question. Now, you asked the question about the expansion of the universe, and that is something we haven't started to play with. For the most part, it's going to affect the future of the universe. The past won't matter much as long as the geometry of the universe is not changing dramatically. I mean, even adding in dark energy did not change very much, because the dark energy, as long as the space-time was flat, adding in or not adding in dark energy in terms of its expansion effects on expansion did not make much of a difference, because it was only in the relative recent past that dark energy started to become dominant in terms of its effect on the expansion. The change that's been proposed by DESI, for example, is a dramatic difference in terms of physics of dark energy, but in terms of astrophysics and cosmology, it's a minor change. But going forward into the future, it'll change the future. We just don't run our simulations into the future.
Yeah, actually, I had a similar question. Maybe you have already answered a little bit, but let me ask it. Like, I mean, how well, I mean, do we understand the distribution of the dark matter, and how much is it matter, like how you put it in the simulation? Like, I mean, what kind of distribution of dark matter you put in the simulation? Does it, like the final outcome, does it matter, or it's kind of irrelevant? Or
so remember, first of all, again, going back to our resolution, the particles that we call dark matter are already almost a tenth, what is it, 100th, just shy of 1 billion times the mass of the sun. So we're not simulating individual dark matter particles, or nowhere near that. We have big blobs of dark matter. The only thing we attach to the dark matter is the fact that dark matter will behave or respond only to gravity. Okay. So that's one thing to remember. That's a limitation of the modeling. But in terms of the initial conditions, we put down the initial conditions the way the microwave background tells us was the matter distribution at an early epoch. But that's we can repeat that, because the assumption here is that the fluctuations are Gaussian random. And so we can vary the distribution within the distribution function itself, and statistically it makes no difference to the outcome. And the fact that we can generate visible universe that looks like the observed universe, given that we start with a statistical realization of the universe, no matter how it's no matter how it's drawn from the distribution function, gives us confidence that at least the dark matter aspect of it is insensitive, if you will. The details of the dark matter properties do not seem to affect the astrophysical aspects or the cosmological aspects of it. So we're insensitive to that. Places where things will become interesting and important is in the central regions of galaxies, for example. If the dark matter is not cold, but it's got a streaming motion to it, then it'll start to affect the shape of dark matter on small scales. But those small scales are much finer than what we can get to. Yeah.
So we had one question, I'll come back to this.
So again, I wanted to ask about the difference in different simulations. So the difference in activity level of black holes. So does it arises because of like the feeding of the black holes? Like maybe because of the way the gas actually feeds, and the underlying dynamical processes like dynamical friction, the way they are modeled, they are different in these simulations? Or it is something more intrinsic to the black holes, like the black hole evolution or black hole mass growth,
Okay.
which affects?
No, it has everything to do with the gas, how the gas is flowing onto the black holes. And it also has to do with how the energy expelled by the black hole is modeled. So let me give you an example of what I mean by that. This is a galaxy, our Milky Way, thin slice. Black hole is sitting in somewhere here. Now, if I was to put energy into the surroundings of the black hole, it'll start to expand. But because the galaxy is like a thick pizza slice, the gas will interact with the energy will interact with the gas and rapidly radiate away. Now, what happens in the real universe? In the real universe, the galaxy is not a monolithic slab. It also is like a sponge. It has these channels. And so the energy would go in, but then the energy would find the nearest channel and take the path of least resistance and get out. We observe it getting out, my colleagues who look through telescopes and study galaxies see these outflows happening. When they look at the galaxy in detail, they see the channels and they see the way the gas is flowing out. Why can't I do it? Because that's way too fine for me. I can't resolve a galaxy like that in the simulations of the kind I've just run. So now I have to come up with a creative way. I cannot let the energy from a black hole vanish, radiate away. I have to somehow get it out of the galaxy so that it can look like an outflow. That is an art, not a science. I have to choose some approximation, some way of doing this, a trick, if you will. How I model that trick makes some difference. Then, if I put the energy in like a bomb and let it go off, or do I shoot it like a fire hose? That makes a difference. And so different simulations do it differently. We see variety of ways black holes manifest their behavior. What we haven't successfully done, and I have a student who's working on this, is to try and capture the full spectrum of black hole behavior in terms of its energetics output and things like that, and put that level of complexity into these simulations to see if that starts to make a difference. And we're finding that it does make a difference. But what's been done so far is because we do not understand the physics well enough, the simplest models have been adopted, and every group adopts a slightly different simple model. And what you're seeing out there is an effect of that. But it's all got to do with gas. Now, I've only talked about gas going out, but gas going in also makes a difference. How that gas falls into a black hole is incredibly important to how much energy it throws out. And that too we do not understand. So it has to be modeled.
I'm an earth physicist, so my questions may sound a bit strange. But so the first thing is about dark matter. Both the baryons and the dark matter came out of the Big Bang, and therefore I expect that there is some relationship between them.
Well, how they emerged, how dark matter and baryons emerged is a question for the particle physicists in the audience. To the extent that we, as astrophysicists, start with the idea that the distribution of matter on the cosmic scales is similar.
Okay.
But then there are photons.
Yeah.
And the photons keep the baryons smooth for the longest time.
So my question is that you estimate the dark matter, pardon me, from the gravitational field that you require to explain the stability of the galaxy?
You can do it many different ways. One is that it's the amount of gravity that's needed to hold the stars in a circular orbit in a galaxy like our own, Milky Way. Our stars are spinning around the center of the galaxy. And if you counted up all the visible matter and asked if I expect the rotational motion of the stars in the galaxy to be held to the center by gravity, how much matter would I need? That's a question that you can directly calculate. And then you ask, how much matter do I actually see? And the answer is I do not see anywhere near enough. I'm basically missing about 70%.
But you use this estimate eventually to put it to your model.
We put into the model the fact that there is 70% dark matter. But we don't set it up as a galaxy in the first instance.
Okay.
The galaxies emerge.
So where do the 70% come from?
As I said, there are at least 3 different ways of estimating it. One is by studying the dynamics of Milky Way galaxy.
Right.
Another is to study the dynamics of clusters of galaxies, where galaxies themselves are moving around, and you can ask, why don't they fly
essentially
apart?
conservation of momenta at various scales.
Conservation of, stability of gravitational structure at different
So my
scales.
last question is that, as you said towards the end, that it gave me the feeling, I don't know whether that's what you said, that a galaxy as an entity exists in a dynamic state by some internal stability, and and the reaction that rebounds on it by whatever it exhales and exchanges with the environment. I may not be expressing myself very well.
No, it's fine.
Right? So, to come to this stage of, I'm sure it's a metastable state, not right.
It's actually a dynamical state evolving,
Yeah.
because even galaxies are constantly merging together. So our sister galaxy, Andromeda, and us
Yeah.
are on a collision path.
But at least for a millennia or several millennia,
Sure,
they will
that's right.
remain in the
That's
metastable.
right. They will be metastable. Yeah.
So how do they reach this stage? I mean, is it possible to say that this is how they will evolve and stop and acquire a certain entity which will be in a metastable state for a while?
Yeah, so that's what we're doing. That the galaxies that we end up generating in these simulations have a metastable state. We can look at the population in regions where there is a lot of galaxies. It's very high density. The metastable state is very short-lived because there's a lot of interaction between the galaxies. In isolated systems, the metastable state could be billions of years. So Milky Way galaxy is an example of that. It's a galaxy whose metastable state has been, several billion years.
And finally, as you model this, do you find that the end result would be, you showed that there are many various shapes of galaxies. Do they all share the same topology?
And can you describe what you mean by topology?
Well, certain characteristics of the surface.
No, they don't, because disk galaxies have a very different morphology and characteristics than
if they
spherical
don't,
galaxies. Yeah.
is it possible to, or is it sensible to ask a question whether the number of possible forms are limited or infinite?
I think that in a gross sense, they are limited. And in the simplest sense, they're limited to two, disks and spheres. The disk shape is sort of, I can try and explain why a disk is ubiquitous in nature, and that goes from planetary disks to galactic disks to accretion disks around black holes. If as gas is falling into these systems, or it's settling down, it's cooling. So it's losing energy, but it's not losing angular momentum. Conservation of angular momentum while leaking energy naturally leads to a disk-like configuration. So disks are ubiquitous. That's why the solar system is in a disk, right? All the planets in the solar system essentially live within a disk. Accretion around black holes tend to be in the same form. Now, once I turn that gas into stars, and then galaxies smash together, I am randomizing the motions of the stars. Stars are collisionless. So now you will end up with a spherical system. So you essentially start with disk-like systems. When you have enough stars built up and a merger takes place, you will start to evolve towards a spheroidal system. And so I would argue that those are the two natural states. Then there is the smallest galaxies kind of look ratty, and we're not quite sure what's dominating them. Explosions of stars could easily disrupt the gas distribution and things like that. So they are very fragile, and therefore they are susceptible to more physics. But the basic physics is what I just described.
Just one last question. You said that there's a black hole in every galaxy.
Yeah.
Is that a prerequisite for the stabilization of a galaxy?
No. We didn't even know about these black holes until very recently. No, we could form the galaxies just fine. The black holes are tiny and have a very small sphere of influence within the galaxy.
Okay, sorry, in the interest of time, I think we'll take further questions to high T. But before we leave, let's thank Professor Babul again. And for you, we have a memento to present. Maybe Professor Bhiman Nath can give the memento. Yes, it's here.
You should come here again.
Yes, I definitely will.
Wish you safe journey.
Thank you very much. Oh, wow. Thank you.
It's from the academy.
Wow, that's very impressive. Thank you. I appreciate that. Books I love, as you know.
Have some room in your luggage.
Yes. Well, what's a kilogram here and there?
Okay, thank you, everyone. Let's have this interaction outside with high T. Thank you.
I hope that was... Yes.
One is, is there still this tension with these JWST
No.
detections of these
Early galaxies?
early galaxies?
Yeah, no.